All right, welcome to day two. You got through day one. Charlie, they got through day one. It wasn't that hard, was it?
I'm so glad we've put this together. This has just been a blast already.
In day one, you learned about the sweeping changes coming to design and construction and the rating systems. And today I'm wearing a jacket because we're going to get serious. Today's all about carbon. We've got two great subject matter experts for these videos.
We've got Nick Kassanis. He's president of Sustainable Investment Group, just an expert with all things lead, commissioning, energy modeling, and more. And we've also got Kristina Bach. She's the co-founder of Blue Ocean Sustainability, licensed architect, has all of the lead credentials, and really is one of the foremost experts on embodied carbon. And again, we're diving deep today, all about carbon.
After you've watched the videos, you can take the quiz, which is 10 questions. It's the first of two quizzes that you'll get if you're going to be going for the LEED and AIA continuing ed credits. Just a reminder, leave us the comments and we'll respond as we see them.
Hi, everyone. Welcome to day two of the Sustainability Challenge. My name is Kristina Bach. I'm the president and founder of Blue Ocean Sustainability. I'm joined today by Nick Kassanis, the president of Sustainable Investment Group, and we're going to take you through the evolution of the carbon story. So when most people think about a building life cycle or lifespan, they tend to think of it in this very linear fashion, where it spends a couple of years in design, a couple of years getting constructed, and then the majority of the life of that building, it's just in the standard operation phase, just kind of chugging along, people using it. It's, turning the lights on, heating the building, cooling the building, et cetera, until eventually, after 60 plus years or so, it gets demolished. The challenge is that buildings don't really operate in that sort of very consistent linear fashion. If you think about it, buildings are much more like living things. Their needs change, their uses change, and they're constantly kind of readapting to what the needs of their occupants are. An example of that is the Dryads Market in New Orleans. It was built in 1849 as sort of a grocery food market where people could come and get fresh produce, meats, et cetera, to serve their basic needs. It operated in that capacity for over 100 years until the 1970s when it was readapted into a big box retail store. Still a retail use, but very different space needs in terms of what they were selling. There wasn't the refrigeration needs that a grocery store had. Different sort of wares and goods required different needs and systems of the building. Additionally, then, about 40 years later, it was readapted again and went through a major renovation to become an entertainment space. It's the New Orleans Jazz Market, a LEED certified theater. So it's about 350 people or so and hosts a variety of different musical sort of performances. And if you think about it, over the course of the 150 plus years of this building, think about all the systems that have changed. We've had internet has come out, all the different technologies that have come up, in addition to just the needs and the use and the focus of that building changing. So realistically, that sort of idea that building just kind of gets built once and then just operates in that standard format doesn't really make sense with how we see buildings used today. Instead, we really see this idea that, as buildings are living things, well, there's a lot of products and materials that go in during the construction phase. From a carbon standpoint, you can't negate the fact that there is still material carbon changes happening in the operational phase that you need to think about as well. I'm going to turn it over to Nick now to talk a little bit more, do a deeper dive into decarbonization strategies and operational strategies that are out there today.
Thank you, Kristina. There are many industry terms around building decarbonization today. It is important to go over some definitions to help us understand what the current conversation around carbon and decarbonization is. Decarbonization is the reduction of greenhouse gas emissions in building construction and operation. We see an emphasis in moving away from on-site fossil fuel combustion, such as natural gas and fuel oil, and a transition to electrification, all with the end goal of utilizing a green electric grid that is built for resiliency. Operational carbon takes into account the emissions budget of a building during its operational life cycle. That includes total energy consumption, distribution of water from the municipality, and refrigerant, which is often overlooked in our eagerness to transition to heat pumps. Although the goal is to reduce overall internal loads and the building's energy use intensity, there is inevitably a minimum threshold of energy consumption needed to operate buildings. The question is, do we offset with on-site renewables or off-site emissions-free energy sources? The difference between these two scenarios is a net zero energy building versus a net zero carbon building, respectively. Ideally, we are choosing our site location, building orientation, and overall footprint such that we have enough on-site renewable energy opportunities to offset the total annual energy consumption of the building. Alternatively, we look to take advantage of regional or national renewable energy sources where there's an abundance due to weather conditions or geographic significance. These are the carbon offsets that can account for the excess emissions generated on site. Not every new construction project can take advantage of on-site renewable energy, especially in the built environment where we have a massive stock of existing buildings that don't have that convenience. Let's talk about building decarbonization trends. Climate disasters are increasing and the federal and state governments are responding nationwide. A growing number of financial drivers for building decarbonization are coalescing. California, for example, has made strides with electrification and decarbonization incentives and codes, whereas New York City and Boston have established local laws setting upper limits on building greenhouse gas emissions, which will be in place by 2024 and beyond. It is not enough to reduce energy consumption and develop on-site renewables, though. While the operational carbon is a major focus, the generation and distribution of electricity is still lagging. Parallel to building decarbonization, there needs to be a concerted effort to decarbonize the electric grid as well. Moving to 100% electric can prove to be a resiliency issue when the grid cannot handle the load. The last thing we want is for another coal-fired power plant to have to turn on during peak demand because our buildings are straining the grid. That is today's reality. One way we can make an impact during the design phase or when analyzing an existing building is through energy modeling. Energy modeling plays a major role in helping establish and define net zero energy goals. For new construction, energy models can prove to be key tools in selecting site location, building orientation, facade design, and more. Through the integrated design process and through parametric analysis of these components, we can determine the optimal design in collaboration with the architect and engineers of record. Utilizing weather normalized data, energy models can help predict what the operational carbon footprint of a building will be during design. For existing buildings, we're working with utility bill data to calibrate our models and how the buildings currently operate. This allows the team to identify inefficiencies in operation and ways to improve both the design and sequence of operations. Massive retrofit projects and opportunities to electrify the building can be simulated to determine feasibility and return on investments. It is clear that these tools can lead to better understanding of current and future operational carbon. What is measured can be improved upon. The pathway to net zero for buildings starts with determining a base system design and looking to improve on each aspect of that design. These iterative improvements can include the architectural design with overhangs and shading, the mechanical design with HVAC system selection and efficiency, and leveraging the building envelope and occupancy scheduling to reduce overall internal load. This methodology allows for the right sizing of equipment and avoidance of excess materials and costs during construction. The last piece of the puzzle, once we've identified all feasible and cost-effective ways to reduce our peak demand and overall energy use intensity, is to identify on-site and off-site renewable energy offsets. As we wrap up our discussion around operational carbon, let's take a look at the loading order for decarbonization. Leveraging energy modeling best practices and the latest technology and innovations, our first goal is to have an efficient design that targets load reductions and electrification. Once we have established the most efficient design based on the project resources, we'll want to maximize the site footprint for on-site renewables such as solar, wind, hydro, or geothermal. After we've exhausted all efforts for on-site renewables, the next step is to procure off-site renewables either via power purchasing agreements, green tariffs, or other means. Lastly, what we can't procure on-site or regionally, we can offset with renewable energy credits and carbon offsets. The need to decarbonize buildings is urgent, but it's only one piece of the embodied carbon puzzle. I'll turn it back to Kristina for a look at carbon impacts through the complete building cycle.
So as we know, embodied carbon is officially the carbon dioxide associated with the emissions of all the manufacturing, transportation, installation, maintenance, and disposal of the building materials. It's supposed to include the carbon impacts of those materials all the way through the product stage, through its use, and all the way up until its end of life, whether it's recycled or disposed of, whatever that might be. But as we talked about, this idea that material changes and carbon and embodied carbon changes throughout the phases, embodied carbon and operational carbon are really two things that you need to be looking at all points in the design construction process. When we look at carbon impacts by phase, for example, during the design phase, you should really be looking at both embodied and operational carbon in terms of forecasting. The embodied carbon is heavily driven by what materials you're evaluating, what you're specifying, what you're putting into your design as your basis for what the contractor should be using to build that building. Additionally, your operational carbon, this is when you're forecasting what do you think it's going to use in terms of its energy and water once the building is up and running and people are occupying that space. When you move into the construction phase, it's when you start getting into those real actuals and basically checking your work or checking your sort of assumptions. For embodied carbon, this is heavily driven by your materials. Material procurement is a big one. And this is really when you want to capture that actual A1 through A3 scope. As we know, a lot of times what we specify and select as our basis of design doesn't always make it into our construction projects. We've all had the case of a contractor substituting some product or material for something else. So it's really important when we get to that construction phase that we're actually going back and checking what materials have been put in and what is that carbon impact, because it might be higher, it might be lower. Additionally, you should be really paying close attention to what the installation process looks like for your contractor. The A4 and A5 scope can vary widely depending on where your project is located, what sort of equipment your contractor is using, what are their standard practices for reducing waste and things like that. So that's something that really needs to be carefully tracked at your job site as you're going through construction. And that goes into the whole idea of construction waste. A lot of people tend to think about waste in terms of just diverted from landfill percentages, how much could you recycle? What they fail to think about or account for is the fact that even waste that is recycled has carbon impacts associated with it. When you're hauling that waste away, you're going to have all those transportation emissions, whether it's going to a recycling plant, whether it's going to a landfill. Additionally, if you're hauling off concrete, for example, that you're going to reuse, but it needs to be ground up, you have all that energy associated with that equipment that grinds it up and turns it into a new product that could be reused. So there are carbon impacts for diversion methods. Every diversion method, whatever that might be, does have a carbon impact. And it's really important to evaluate not just is it getting diverted from landfill or not, but how am I diverting it and what's the carbon impact of that process? Or might there be alternative options available to me in my location that might be more carbon effective or efficient? When we get to the operations phase, operational carbon becomes the thing that everyone kind of thinks about. They understand it, that the building is now up and running. You're going to be tracking your energy consumption in terms of water, waste, fuels, etc. at that operational level. What does it take to actually use the building? The challenge is that embodied carbon is still this kind of progressively growing carbon footprint. Embodied carbon doesn't necessarily go away or change. And while the amount of, sort of changes that it undergoes will decrease, it doesn't completely get eliminated. So the initial impact of what you spent in your in terms of carbon cost to build the building does decrease kind of on a year-over-year basis as the building lifespan ages. However, when you start getting into those material replacements, the upgrades, you're doing new tenant fit outs, new construction work, just maintenance, you're going to paint at some point, you're going to replace the carpet at some point. All of those have material carbon impacts, waste carbon impacts, et cetera, that really change what that material sort of embodied footprint of the building is. It's not a static one and done sort of process or evaluation when the building's completed initially. And when we move towards the final sort of, stage or end of life for our buildings and we start to demolish them, whether that's being disassembled and, recycling or going straight to landfill sort of a process, we really want to be looking at the final results. What was our holistic carbon impact for that project throughout its entire lifespan? We're looking at the embodied carbon of that materials based on how did we actually divert them, not how did we think we could divert them or what might have been recoverable, but what did we actually do with those materials when we took that building down, so that we can come up with kind of that full scope, holistic look at how much carbon did that building use across its entire lifespan and how accurate were we against our initial predictions in that design phase. I hope you'll join us in our next class later today for talking about embodied carbon analysis, how it currently works and why it needs to have a reboot, some of the challenges that go into the current calculation method. Thanks so much for joining us.